For centuries, we viewed the universe as a giant machine. In this world, if you knew the starting position of an object and the forces acting on it, you could perfectly predict its entire future. But when scientists peered down into the world of atoms, that predictability vanished. They found a microscopic casino ruled by chance, where particles act like waves, and outcomes are governed strictly by probabilities. This reality was so counterintuitive that foundational physicists rejected the idea. Albert Einstein insisted that the laws of physics shouldn't be based on a roll of the dice. Because these bizarre rules only seem to apply at the tiniest scales, it's easy to treat quantum mechanics as a mathematical puzzle that has nothing to do with our daily lives. However, engineers have spent decades harnessing this microscopic chaos to build the modern world. Your smartphone is a quantum device. Its ability to process information relies on the very behaviors Einstein found so troubling. At the scale of an atom, electrons orbiting a nucleus inhabit specific, rigid energy levels. They can't simply float anywhere. They are restricted to these distinct tracks. To move between these tracks, an electron must absorb a photon containing the exact frequency required for that specific leap. This resonant frequency, the precise energy needed for that jump, is a universal constant. It provides an ultra-precise, unchanging pendulum that scientists can use to measure the passage of time. Modern optical clocks use elements like strontium to create a quantum pendulum that swings millions of billions of times every second. This temporal precision is what allows the GPS network to function. By knowing the exact time a signal takes to travel from space, your phone can calculate its distance from multiple satellites and pinpoint your location. A standard light bulb produces a jumble of photons moving in different directions at different frequencies. But if a specific photon passes an excited atom, it can trigger that atom to release an identical duplicate. By trapping these atoms between mirrors, scientists create a chain reaction that forces trillions of photons into perfect synchronization, sharing the same color, phase, and direction. While this focused beam of light is used for scanning and communication, its fixed wavelength makes it the ultimate ruler for measuring microscopic distances. At the LIGO Observatory, lasers are split and fired down miles-long corridors to detect tiny fluctuations in the fabric of space itself. Taming these properties of light has given us a tool sensitive enough to record the gravitational ripples of black holes colliding billions of light-years away. Researchers are now moving toward even more elusive behaviors: superposition, where particles exist in multiple states at once, and entanglement, where particles sync their behavior across vast distances. Utilizing these states requires extreme environments. Dilution refrigerators cool superconducting metals to near absolute zero, protecting these delicate quantum connections from being destroyed by heat. This hardware enables a different kind of computation. A classical bit operates like a light switch, restricted to being rigidly set as either a 0 or a 1. A qubit uses superposition to exist in a fluid state of both 0 and 1 simultaneously. When multiple qubits are entangled, they can perform highly complex calculations that standard processors are unable to simulate. The complexity of this system is immense. Describing the state of just a few hundred entangled qubits requires more data than there are atoms in the visible universe. A century ago, the world's leading minds viewed the quantum realm as a source of deep anxiety and a challenge to our understanding of reality. Today, that theoretical debate has evolved into an industrial toolkit. We have moved from questioning these laws to using them as the basis for our most advanced technology. Perfecting these tools, from stable lasers to error-correcting qubits, allows us to manipulate nature's foundational code directly. While the microscopic universe defies our classical intuition, embracing its weirdness is what empowers us to engineer the future. To see how these and other discoveries are shaping our world, subscribe and engage with us for more deep dives into the science of our reality.